All right, so we're back on my YouTube lives. And we're keeping it ourselves. It's, yeah, I know, it's not on topic, I understand, but I cannot tell the difference without eavesdropping. Also, if you cannot read it, it's on your quote as well. If you don't know, you shouldn't ask to read it. If you have questions, you can ask me. I'm getting paid for answering. No, we can discuss about the answer afterwards. Let's not do it during the quiz. of real-time analysis here. And it says the average score is 65%. Meaning you got on average one question right and one question half right. It's kind of weird, right? Okay. All right, we'll see. I cannot discuss the solution of the quiz right now because people are still taking it. I left it open till 11. So what I'm going to do is if you have questions, we can answer them if you have questions about the exam, I can answer them at the end of the recitation, or no, you don't. So I want to start by not really reviewing chapter 1 and 2. That's kind of your job, right? What I want to do today is I want to ask questions, or I want you to solve problems related to those two chapters. So it's important that you're prepared before class. That's why you get one lecture off, right? So it's not that you're having free time, it's that you're supposed to study and be prepared. Right. So I will review, or I will remind you of the most important concepts of chapter 1, which was about units, right? So units means that it doesn't change the math, it just improves our way of communicating to each other. And so when I say, I don't know, the fish I caught was 15 sums long, you're like, whose sums, yours or mine, right? So we need some kind of standard, something that we can compare. And so this standard has to be something that you have access to as well as me, right? And so it also has to be reasonably accurate for the thing that I'm telling you, right? If, for example, I could say the fish I caught was about 1/10 of a tree size, right? And you're like, no, there are big trees and small trees. What do you mean? So it has to be accurate, at least to determine the length of a fish, right? So that's why for a long time, this was accurate enough. A cubit was accurate enough to be like, well, your fish was 2 cubits long. So it also means that it changes over time, right? It changes with necessity. For example, for a long time, people didn't need clocks, right? Because they just got like the bell on the church tower and it would tell them now it's midday, and now it's time to wake up or something. And that was the only 2 time references that they needed. And now we're interested in measuring stuff with nanosecond precision because, well, we're getting faster. So that means that it cannot change with time. A standard has to be invariable. It cannot change with temperature. For example, your ruler will increase by about a micrometer if it's made from metal, if you heat it by degree C. Okay, so that means that today your ruler is a micron shorter than tomorrow because your temperature changed by a little bit. So that's not important, right? Because you're not interested in measuring a micrometer, you're interested in measuring a centimeter. But imagine you're building something that has to be more precise than that. All right, so measuring things. And so what we're interested in are SI units. I apologize to the American imperial system. Americans and Nigeria, I think, are the only 2 countries that don't follow the SI system. I'm not going to fight on that. Since 1976, they're supposed to follow the SI system because everybody else does. But again, so what we're interested in for now is only 3 quantities: length, time, and mass. We're going to learn. Another one later on, but everything else can be derived from those base quantities. Right. So, and then I went on about what a meter is, and what a time is, and that's, you cannot just use 24 hours, or you cannot use like the rotation of Earth to determine the time very precisely. And that mass is a weird thing because it doesn't have an equivalent in nature. We haven't referenced it with respect to some equivalent in nature. we are trying to have it be referenced to 12 carbon atom, to carbon 12 atoms, but that means we have to make something first and be like, this now is a kilogram, because it has exactly 600 times 10 to the 23 atoms in it. So we have to count enough atoms with enough precision to be like, okay, this is our new standard. I'm going to put it somewhere, and now you can compare your table to this. So it doesn't exist yet. Right. And so I introduce, so units are not changing the math. You are welcome to calculate with this. You're not going to make a mistake. So basically, what we have done in the first chapter is not changing physics. It's just there to improve how we're talking to each other. And so the first thing that we're doing is we're making this number easier to read. Okay? No physics involved. This is just for my convenience, because I have seen people writing this. And then I'm like, how many zeros, or a million, a billion, or 3 billion? Okay, fine. So that's very annoying, especially if you're not grouping it like that, right? So I would like you to communicate more efficiently. And that means we are not changing the number, we're just making the number easier to read. And we're doing that by putting like all the zeros as an additional unit. Unit meaning that it doesn't change the numbers, it's unity, it's 1. You can multiply anything by 1, you're getting the same number back. Now I multiplied it by 1,000 over 1,000. So 1,000 over 1,000, 1, right? And so what I'm then doing is taking the 1,000 over, so that gives me 25, and I leave this to communicate. So I'm saying 25 times 1,000. 1,000. Right? So I can say 25 times 10 to the minus 3. And now you're like, why didn't you use 10,000 over 10,000? Then I would have gotten 250 times 10 to the minus 4. And again, unit. You can multiply it with anything you like, as long as you're dividing by the same number. You could have taken 25 times pi over pi, and then you would have gotten a really weird number times 1 over pi. Fine. It's just that that is not efficient communication. So that brings us to the second part, which is significant figures. Significant figures means how much of the information is really important. And I say 3. That's as much information as is necessary for me to understand what you're doing. You get 3 numbers with a period in the middle. And I will not read before or after that. Significant figures meaning that you probably need 1 in front of the period and 2 behind the period. Okay, so I don't like 25 times 10 to the 3, 10 to the minus 3. If possible, I would have liked 2.5 times 10 to the minus 2. So why don't we just do 10 to the minus 2? That brings us to communication again. We like to break them down not just into numbers, but we give the numbers names. My 4-year-old is really excited about that because you just add kilo to anything and it's 1,000 times more. Right? So he's telling his brother that kilo hates him because that's 1,000 times more hate than you could put into normal words. And so he knows all the way to Gogol, which is 10 to the 100. And so basically you cannot beat him anymore. But the ones that we need are if you see, in 3, in steps of 3. Again, 3, that's all the information that you get. 10 to the 3 is kilo, 10 to the 6 is mega, 10 to the 9 is giga. That's giga, depending if you watch Back to the Future or not. Giga. And then you go 10 to the minus 3 is milli, 10 to the minus 6 is micro, 10 to the minus 9 is nano. Maybe you still need pico. We're measuring very small currents, we go to femto, but atto is something that it's about 10 electrons. We're going to get back to that. So this is the range, and now we understand why we like 10 to the minus 3, because it's milli, right? So that's why we were saying 25 milli instead of going, well, you could have gone 2.5 centi, right? But centimeter is, or centi as a unit, is the only one that doesn't follow really the rule of threes. That's because centimeters is the only thing that we kind of need, where like a centimeter is about, it used to be the width of my thumb, but that was like 20 years ago, okay? But probably the width of my index finger. So, all right, so we get that. And so the same is true for communicating length, time, or mass. We give it a unit that we can, communicate more clearly. Right. And so that means that we can do the same thing with unit conversion as we just did with number conversion, with adding unity in any quantity you like. 60 seconds is 1 minute, right? So it's 1 minute over 1 minute. It's 1. So we haven't changed the math, but what we can now do is this minute will cancel against that minute, and just left with seconds. So that makes my life much easier because I can interconvert between different units. And so we're going to see that now. All right, so this is a picture of Boston, and MIT is actually not in Boston. MIT used to be over here, but then it got too small, and so it moved over to Cambridge. Harvard is not in Boston either. Harvard is not in that street because they don't. I don't know. I think they don't want universities in downtown Boston because it's really cramped and small. So, anyways, in order for you to go from MIT or Harvard, from MIT to Boston, you have to get over the Harvard Bridge, which kind of insult to injury, right? It's like you're not in Boston and you have to cross the Harvard Bridge to get there. So, not pleasant. Well, it's a very beautiful view because all the tall buildings are over here, and so walking across is very pretty. It's also pretty long. And how long? So one day, or let's say in January in MIT, there's something called Independent Activities Period, IAP. And it means that after Christmas, you come back to MIT and you don't have class until February. So basically, the whole month of January, you just get to do whatever you want. And for undergrads, that means that once they turn 21, they get drunk. So this is the time when you see, kids being drunk on campus. They're not allowed to be drunk. They're not allowed to get drunk on campus, but they are drunk on campus. So don't know where they get their alcohol from. It's very hard to get alcohol in Boston because it was built by Puritans. So they card you. You have to bring your ID. You have to bring your passport if you're a foreigner. Or you can get a liquor ID, which is a weird concept. You have another card that is just there to say you're old enough to drink alcohol. And they carded everyone. My mom came visiting, and they carded her. It was like, if you think that I'm under 21, they're like, if we don't do it, we're going to get sued. And so everybody gets carded. But undergrads have their ways of getting alcohol, and so they got drunk one day, and they wanted to measure the length of Harvard Bridge. And they had no room. Instead, they had a guy named Oliver R. Smoot. Oliver R. Smoot is now in NIST, the National Institute for Standards. But back then he was an undergrad, and they're like, all right, what we're going to do is we're going to put Oliver R. Smoot flat on his back, and that's one length unit. And then we're going to have him stand up, and get one foot to head, basically. And so they measured the whole bridge, Harvard Bridge, foot to head of Oliver R. Smoot. And it's interesting because this happened in the 70s, and it's still, the marks are still there. Every year, volunteers will add the marks back on, or will highlight the marks back on the bridge. So I can tell you that like about here is about 30 smooths. That's when you know you're getting to the site. So they have like a 30 SM, and a smooth is a real unit. You know, it's not a crazy. It's not just that they made that crazy prank. It was that it's a unit. You can look it up and they list web page. And so our smooth was 170. And so they measured the bridge to be 364 smooth and 1 ear or something. Oh yeah, 364.4 in the ear. And that was extremely precise, considering that they used a person and they were drunk, right? So that's the promise of MIT engineers. So my question is, how long is Harvard Bridge in centimeters? So find your group, either in face or on NTU Cool, and discuss. And at the end, submit your common answer, okay? 3 people should agree on one answer at least. And then submit that in the discussion forum. Okay? I will go through the discussion forum to so I'm not sure if you heard this. We are answering that question over there. I should probably put that online. So. You don't have to worry about the ear, okay? Just get 364.4. No, so you discuss, you find an answer, you put it on the recitation discussion board in your group, right? Yes. So, were you here last Thursday?
Yeah, I was.
So you joined the group, right?
Yeah, I joined.
Awesome. Just put it into that group. Just as a response. Huh? Yep. Oh. Recitation discussion group before. We did that last Thursday, but there are new students. So the first thing that we have to do is find a group. Uh, so if you go to Entry Pool, you'll see that there are discussion groups, and you can either try to join one or you can create your own. Just make sure that there are 3 people. So just try to join one, and if you get kicked out, it means there was already 3 in there. Just press. Okay, so if you don't have a group, you somehow magically join one. I don't remember. How did that work? So just, can you see the discussion? So before you do this one, you have to first join a group. Where is this? Well, see, yes, so you can join that one, but that doesn't happen. You want to join a group that has a couple of students. Or you can make your own group in Ireland. Yes. Just as a request. Yes. So simply add a reply to the discussion group. I can access all of them since I'm the admin, so I can see your replies. Hold on. Yes, hold on for a second. So if you haven't joined a group, go to Enter Pool and click on People. On top of People, there's Groups. People. It's possible that it doesn't go out in no, you should be able to join it with the video. You can find out which group are you? People. You can add your own group plus.
我们上次那个，我上次那个 Q 是哪一个？哪个？然后呢？点进去吧 ，Recitation。点进去吧。没事。点进去啊，看这个就可以啊。可以。Henry something.
Still figuring out that problem. So you're saying type. Are you inside the recitation or the student group? We had that problem before, that in student group, so type R is in student group, not recitation group. You have to log into them. So please make sure that you're in the recitation group, right? We have 2 groups, a student group, I cannot delete that one, and a recitation group. I want you to join a group in recitation group. if you haven't already.
Probably some of our answers.
So once you're in there, just as a reply in the discussion, you go back to the discussion board and you answer a reply.
Are you in groups or?
No, it's in it's in discussion. Go to the front page.
This one, right?
Yes.
Or,
Yep.
And then just reply.
Just reply. All right. More technical problems that we have to solve? No. Good. Now we get to the physics of it. I'm gonna randomly pick an answer. So the answer that I got from somebody is 6.19 times 10 to the 4 centimeters. Does that make sense? So the question is, does that make sense? Can you, do you have a feeling for centimeters? That's the first question. Maybe not. So maybe we should put it in meters, right? Just so that you get a feeling for it. So how many meters would that be? $61,000 centimeters is how many meters? 619. Right? Because it's 6.19 times 10 to the 2. How did I get there? 6.19 times 10 to the 4 centimeters times 1 meter is 100 centimeters, or 10 to the 2 centimeters. And so 10 to the 2 cancels, subtracts 2 centimeters against centimeter, and so I'm left with 6.19 times 10 to the 2 meters. Or if like that, you could say 6.19 times 10 to the 2 meters, 10 to, like 100 meters is 10 to the 2 meters. Right, again, I just introduced the unit. So I get 6.19 meters. So 619. So that was just to see if the answer makes sense. It's over half a kilometer. That's pretty long. This is 1,000 feet. And this is like 2,300 feet. Does that make sense? How much is 2,000 feet? 2,000 feet. 1 foot. 1 foot is 30 centimeters or 0.3 meters. So you get to about 600 meters. So, okay, 600 meters makes sense. How did you get there? So all this was just to evaluate if your answer makes sense. Because you should not be done by just writing down a number on your exam and being like, now move on to the next question. You should somehow confirm that what you're saying kind of makes sense or completely out of the expectation. Right? Imagine you're calculating the size of a planet and you end up at 1 kilometer. You're like, all right, I did everything, this is my final answer. Doesn't make sense. Doesn't make sense that a planet is 1 kilometer. I'm not sure. How big is Earth? Right? So have a feeling for what you're working on. So that was just that it makes kind of sense. How did we get there? Well, again, we know that the Harvard Bridge is 364.4 smooths, where 1 smooth is 170 centimeters. 77. And so all you have to do is calculate 364 times 0.4 times 170 centimeters. Right? So you're like, you probably got there just by a gut feeling, what you have to multiply, right? But take this seriously because this is going to be important when you're converting units, also when you're checking units. So, yeah. All right. Let's do a little bit more physicsy. A certain physical quantity is calculated using A, which is speed, B, which is something, and B and C, which are distances. Right, so the question is, what is the SI unit for the result? You understand the question? This was one of the options for the mini quiz. So I should put this in. Then I was like, apparently out of 2 questions, you only got 1.5 correct. So let's keep this till the next time. Just put it on and you're cool. Let's do 3 minutes. Same thing, just back on into your pool. Just the recitation technique. Same recitation group that you just joined. Yeah. So open. It's not open. It's only open to you. Your 3 group mates, and but I can see. You can only see the ones inside your group. No, they are not. Really? Can you see responses from other people or just within your group? Oh, you're special. I'm not sure. You should only see the ones within the group. Is it because you haven't joined the group? I haven't joined the group. Oh, okay. Now you don't see. It's possible that, well, yes, I think some of you are posting to the general discussion board, not the group recitation group discussion board. And so then it's open to everyone. Yes, you are very welcome to go to the bathroom. Not your mom. Want to do it together? Units are just like numbers, right? That's what we just realized. We can cancel numbers, and we can cancel out units. So that means that we're left with the unit for speed, so we have something that looks like unit for speed, a unit of speed, sorry, which is distance traveled per unit time interval. So what's a unit for distance? For unit time, so distance over time. And then we have distance minus distance. Nice, so doesn't that just cancel out? Meters minus meters. It doesn't, right? Because we haven't specified how many meters. It only cancels out if there's exactly that many meters here and there. So it's not like it's canceling out. So for subtraction, this can lead to weird results. Imagine C would have not been in units of distances. What if C would have been in unit of weight? You cannot subtract a meter from a kilogram, right? They're two different things. So that means that if you're seeing a subtraction or an addition, it has to be the same unit. This is kind of useful because many times you start messing up and then you start adding things and you're like, oh yeah, 3 plus 4 works. But if you see 3 meters plus 4 kilograms, and you know that something went wrong inside your stock. So, all right, so we cannot do that, but at least we know both of them are meters. And so I multiply meters with meters second, and I get meters squared seconds. Is that a useful unit? Not really. I've never seen, like, this is area per time. Maybe it's like how fast you eat a pizza, but other than that, that's the other thing. You look at the unit and you see if it fits your solution, right? Imagine you're like, I want to know how fast the car went. So I calculated speed times distance. And you end up at area per seconds. It doesn't make a lot of sense. So units are important because they can keep you connected to the problem. All right. So questions about units. We have to memorize the different prefixes. You should know them already. It's kind of like common parlay, right? Like we use a kilogram all the time without specifying that that's 1,000 grams. So I think the ones that are highlighted, I would just memorize. Other questions? How will I grade this? I will grade how you're responding, right? So you're like, I put it on the discussion board, what's going to happen? I will have the TA comb through it and get the right answers, and then be like, okay, this group got the right answer. And then it will be added to your, your 50% grade. If you're attending recitation. Other questions? Okay, no other questions. So that brings us to part 2, part 1. We're not going to finish motion along a straight line probably, but we're going to carry that over till next Thursday. Yeah, next. I'm hesitating about the Thursday thing because we're almost at full capacity of this room. Thursday room is smaller than Tuesday room, so I'm thinking of moving it over. But currently we still have like 8 seats, so we're good. We'll see. If it gets more full, we're gonna change it. Not next week. So next week, Thursday, we continue motion along a straight line. The simplification that we're making is a point-like particle, which means that we're not considering how the particle rotates. We're not considering how it, if it hits something, is it going to deform? We're only assuming that it's an atom, where all the weight of the object is concentrated. So this is kind of like Ant-Man. Ant-Man, like he gets small, but his weight stays the same. So that's what we're doing here. which is weird, right? Because that would mean that all these miniature, like he should just sink into whatever floor he's walking on if it's small, right? Because he now has a tiny, tiny area but the same weight. So his pressure must go through the roof. But anyways, the concept of particles is that it's a simplification. We don't have to worry about the shape. And we don't have to worry about where forces will act on. We just say that everything is concentrated. And so then we're saying a particle moving to the right is going to be positive, and moving to the left is negative. I'm not sure if that comes from right-handedness, but it's kind of discriminating against left-handed. So anyways, again, this is a convention. It's a standard, right? The same way that you could say, I don't like meters. Meters are too long for measuring noodles and too short for measuring trees. I want my own unit. You can do that. You just have to convince enough people to follow your standard, like the schools, right? So that means that a position can be positive or negative. There can be positive or negative from, like, from an origin. It can be on the left or the right hand side. And we're introducing something called displacement. Displacement means that, that we're going from one point to another point. Yes? So we're changing position. And when we're changing position, now we have a direction, right? If I go from your left to your right, I went that way. So that's for your right-hand side positive direction, right? Whereas if I went the other way around, that would be negative direction. Right? So that means that my motion now has two information. One is I moved along the table, so that's the length that I moved. The other one is you moved in positive or negative direction. So we introduce a vector. A vector is a quantity that has a magnitude, length of the table, and a direction, left or right. Yes, so that's going to be important when we start talking about three-dimensional motion. But we're not there yet. So we introduce displacement, and we introduce velocity. But what I want to do here is take a step back and actually give you a reason why we're so excited about position and velocity and acceleration all being connected. And that is called the position time graph. So what we're doing is we're plotting the position of something versus the time, right? Position time graph means from the name you can already tell that position has to be on the y-axis because it's the first thing we're saying, and time has to be on the x-axis. When I say current voltage diagram, it means that current is on the y-axis and voltage is on the x-axis. So we will plot a point as a position on that plane, right? I measure something at 200 seconds, it is 450 meters away, it will get a point here. Yes, so why is that important? Okay. So that means we can describe a motion as a sequence of snapshots, where like you close your eyes, you open it again, and the ball is somewhere else. You close your eye, you open it again, and it moved again. And so this is the times, and this is a position. How would the position time graph look like? Position time. We should give it a unit, otherwise we're getting points subtracted in the exam. You write the right number without a unit, that's not the right answer. My previous TA was pretty harsh about that. He subtracted, he gave you, I think, 3 points or 2 points for the right answer, and 1 point he subtracted if you got the right answer, but not the unit. So I was kind of, I thought that I was mean, but he's correct, right? He's saying that it has to have a unit. All right, so how does that look like? So at 1 second, it's at position, at 0 seconds, and it's at position 0 centimeter. At 1 1 second, the position 1 centimeter. At 2 seconds is at position 2 centimeters. At 3 seconds. So every second moves a centimeter, right? So, and the corresponding position time graph is a line. Why is that important? Well, because I don't really need to know all the points of a line, right? I need to know one point and the angle. And so the angle is just the slope. And I just say that it started like this is my original position, my starting position. So I know these ones, then all I need to know to describe a line is its slope. Remember slope? M equals y2 minus y1 over x2 minus x1. Yes? Who has not seen that one before? Like this is for y equals mx plus n. Or you like ax plus b, and this is a. Okay? So if I wanted to get the slope, that would mean that I get position 2 minus position 1 over time 2 minus time 1. Right? Sorry, nobody can see that. Right? And so I call this quantity, like the change in position over the change in time, or the displacement over the time taken, I call this velocity. So now you understand that all I need to describe a motion is its velocity and its starting point. And then I can describe the motion at any other time. Right? Nice. So this is why we're excited about position time diagrams. But you also see that, yeah, okay, so velocity, you can read off which one is faster, right? This one moved farther in the same time. Like in 2 seconds, it went 5 meters, and this one only went 2 meters or something. Right, so a steeper slope, a higher slope means a higher velocity. You also see that, oh, right, okay, cool. I like this one. It's a story, and so I'll read it for the online people, and read it yourself. So it's about a dog who's walking east. Where's east here? He's walking east, and then he runs west, and then he stops because the cat that he was chasing disappeared. And then he sees a motorcycle and he hunts that one. So he is running east again. And then he gets tired and stops running. And so which position time diagram represents the dog? Imagine you put a GPS tracker on the dog and you see that, right? He moved on one line basically. Just first you moved to the right, then you ran to the left, then you ran to the right, and then you stopped. Right? Let's do this. 5 minutes. If you cannot read it from the back, you're welcome to just walk to the front. Also, then you're getting the exercise. There's very little talking going on in this call. There's a lot of talking going on in that call. I prefer that one over that one. Why don't we try together? So, in addition to my lecture, so I put down, I uploaded the lecture slides. I uploaded a narrated version of the lecture slides, and I uploaded a couple of links. Right? Have you looked at those ones? They're basically telling you, like one of the games is named at motion, I think, which is like, how would a position time diagram look like if the dog stopped? Right? How does it look when a dog stops? It doesn't change. It doesn't change position over time, right? No, that was an immediate response. It's really cool. And position doesn't change over time. This is stop, right? We were just saying this is fast, right? The velocity is high, and this is slow. So we just have to. What did we miss? Oh, going backwards. How would it look to go backwards? You're changing the position towards smaller ones, right? You stand. You could say, "Oh, I go to negative positions," but we're saying we're only interested in the slope, right? So the slope of this and this is the same. So this is backwards. So that's the first thing that I would do. I would kind of determine which, like, what's the possible things I could read from this. So for example, this means backwards, right? This one is weird, this means stop, right? What does this mean? I haven't written that one. What's that? It is basically it's at the same, like during the same time, it's at two different positions. Nobody watched Jumper with Hayden Christensen, I guess, but that's what it means, right? You're at two positions or at all positions at the same time. So this is not possible. Impossible. Because you would have infinite speed. Your slope is infinite. Your speed is infinite. Unless you're the Flash, you cannot be in two places at the same time. So this one is unphysical, right? You stop and you just reappear someone, then you just reappear somewhere else, and then you reappear. So that's the other thing that might be useful. This is called multiple choice, right? Because it has to be one choice out of the multiples. Also, one interesting question would be, do you have more than one choice? Like in the exams that I'm asking, can there be more than one? There cannot, okay? That means you just have to rule out three, and you're left with a fourth. So I just ruled out one, right? So what I would start with is looking at what's the difference between them, right? And I would actually start with the back. I mean, you can start from the front and then rule out, but I found that this is nice. So D, C, and A all stop with a flat part, meaning the dog stopped, right? But the one in front of it, right? So what we know is that the one before the dog gets hired and stops running is that he runs due east. Due east means eastwards, right? So it must be a positive slope. Wait, the last one is this one, the negative slope. So this one was running due west. So it cannot be C. So we're only left with A and B. Now what's the difference between the two? If you look carefully, the only difference between them is that this one has this flat part and this one doesn't. So the dog initially walks to east, fine, and then he stops. Whereas this one just starts running due west. Right, so that's why position time diagrams are useful, because it describes the whole story in one picture, right? So, nice. I'll do that one. So, we say that the slope in the position time diagram is velocity. And so this is nice because we can get directly from a position time diagram, we can get a quantity that we're interested in. But now the question is, what would happen if my position time diagram, I'll take that one away, turn YouTube to me. What if my position time diagram didn't have a nice a nice straight curve. What if I start and stop and start and stop and start and stop and start and stop? Okay? What if I do that really, really fast and I get something that kind of looks like that? Now you cannot say, well, the slope of the line is my velocity, because the slope of the line changes all the time. All I can say is, well, if I just cared about what happened at the end of the race, it's fine for me to, I don't care if he starts and stops. I just want to know how long did it take to reach 100 meters, right? Nobody's seen Monty Python silly walks, right? But basically there was a race for people that walked funnily, and it turned out that the one that basically stayed and then he just started sprinting, he won. Monty Python is real, but the point is, we could not, if we just looked at these 2 points, we could not tell the difference. Right? We wouldn't know if he started and stopped and ran, or if he just slowly walked. Right? That's the idea of the turtle and the rabbit. You know that story? So if we only care about 2 points, then the slope connecting the two is called the average velocity. But what if we wanted to know what really happened? Now we would have to take the slope at every point in time to know if it slowed down, if it went backwards, basically what the dog did. Oh yeah, that's the other thing. How far did the dog actually end up from its house? It's not that number. We don't care what it did, it ended up this far east from his house. It didn't end up at his house, right? He's lost. So we don't care what he did during the time. It's just like he's now 100 meters away from his house. So the average velocity is during a whole day he moved 100 meters. Actually, we don't even care if he moved east or west. It's just like he ended up 100 meters away from his house. So we don't even care about the direction. We just care about the magnitude. So in that case, it's called speed or average speed. Velocity has a direction, speed doesn't have a direction. It's not a very useful thing to know that it moved 100 meters and not care where it moved. So please don't use speed in describing motion unless you really mean I'm only interested in how fast he went. Most of the time we're interested in where did he go, right? So we want velocity. So speed not very useful. Velocity, average velocity not that useful either, unless you care about the outcome. So we need to calculate, we would somehow need to calculate from a position time diagram the average, the instantaneous velocity. How do we do that? I mean, we were saying this is the slope. Can we say something about the slope of that wiggly line? We can say the slope changes, right? And so that means if we calculated the slope at every point, we would get velocity time diagram. And so how would that look like? Well, it's going faster, then it's slowing down, then it's going faster, then it's going down, then it's going faster, then it's going down. It's never going backwards. Great. And how did I get there? We're saying that this is a slope. What happens if you make the slope smaller and smaller and smaller and smaller? If you don't want to get a triangle over everything, but just like an infinitesimally small, tiny, tiny triangle. It's then the slope of, so we were saying this is delta x over delta t, which, If we wanted to make it small, if we make that delta x smaller, we're going to call it dx. And if we make the delta t smaller, we call it dt. This is my instantaneous velocity. What's that called? Derivative, right? Who is uncomfortable with derivatives? It will then get more complicated than taking a derivative of like a square. Okay, there will not be more complicated functions that you have to take a derivative of. But if you don't remember how to take like a derivative of, I don't know, 4x squared plus 6x plus 7, and you might want to look into that. Okay. But wait, now we're getting a wiggly line here, we got a wiggly line there. That means that something caused this to speed up and slow down, right? And so the change of velocity over time seems to be interesting as well, right? Because something made it slow down, something made the cat show up. No, something made the dog speed up, and that was the cat, right? So we're calling this one acceleration. Acceleration is the change in velocity with time. Okay. And so we can have an average acceleration and an instantaneous acceleration. And so if you, so that means that if we took the derivative of that one, t, we're seeing that it's speed. Like it accelerates and it decelerates. Accelerates and decelerates. This is slow. Down. Acceleration. What's the unit of acceleration? It's the unit of velocity over the unit of time. All right, so that's why we're interested in it, because these three graphs are directly related. You just need one, you get all the other ones. You take a derivative of this, you get velocity. You take a derivative of that, you get acceleration. So this one is including all the information that I would need about how does it move, how fast does it move, and why does it move. So that's what makes it interesting. But you also see that we could start with a simple, this seems to be the hardest case, right? Slow up, speed up, slow down, speed up, slow down. What if we just had a simple case? Where the acceleration was a constant. Acceleration being a constant means it speeds up at the same rate. Every second, it gets 1 meter per second faster, right? Or every second, you get 9.8 meters per second faster. That's what happens when you fall out of a window. So if you catch something in the first second, that's already hard enough, because that's like grabbing something after 30, like at a speed of 30 kilometers an hour, right? So I wouldn't want to do that, but it's much easier than grabbing onto something after 2 seconds. Because now you are, we're going to get back to how fast you are. So if I were looking at a constant acceleration, how would that look in a velocity diagram? Or maybe the other way around, how would a velocity diagram look like that has a constant slope? Right, because we're saying like slope of velocity is acceleration. What's a constant slope? I mean, we're just scratching your nose. Yeah, it's like you were pointing, like it's a line. Right? Why? Well, because the derivative e f at e t as a constant That makes sense, right? Because we take x, we take dx of x, get a constant. Or maybe you remember the other way around. How do you get from a derivative to the original? Integrate, right? What's the integral of a constant? Yes, sorry, yes. I was answering my own question, and you cannot see it over there, right? So, the integral, where do I put it? Integral of a constant is a linear increase, right? So now the question is, can we play that same game here? So how many of you can integrate? So I would say this is the integral of x. Well, integral p dt, but people don't like to change variables. So I'm just going to go x EX. Right? I'm already making the math hard enough. Who can solve that? Right, 1. Then we'll do it by hand. This is not the only way to get there. We can simply go and do it with simple math. So we're saying acceleration is v2 minus v1 over t2 minus t1. I'm going to set t1 to 0 because it's already annoying enough. And so now I'm saying velocity is x2 minus x1 over t2 minus 0. So what I would like to know is how is x related to a? So I can solve this, right? I can say e2 is a times t2 plus e1. And now I can take that and I can put it in here. So this is not v2. This is the average velocity, right? That's how we do it. But the average velocity is 1/2 v2 minus v1. Sorry, plus v1. Right? The average. And so we can plug in v2 here. Where do I put it? I cannot put it too low because then you don't see it. I cannot put it right here. So the 2 would be the average, 2 times the average plus v1. We just got v2, that's a times t plus v1 equals 2 times the average plus 1 cancel. So I get a times t, or a times the half the average. And so I got that v equals x2 minus x1 over t2 minus 0. So take this is the average. So plug that one in, I get 1/2 a times t equals x2 minus x1 times t. I forgot the 2's, sorry. And so I get x, and I forgot the v1. x2 is x1 plus v1t, I forgot, plus 1/2 at squared. We would have gotten to the same thing if we integrated that one, because that one would be 1/2 x squared. So this is the connection between the different position, velocity, and acceleration time diagram. A constant acceleration gives you a linear slope, gives you a square. And so you're like, Why do I care? This is hard math. It doesn't get harder than that for a while, right? Because constant acceleration is something that you need a lot. Constant acceleration is what happens if you just drop out of a window, or if you drop an apple onto somebody's head. So this is like, how to say, these are kind of the fundamental equations that you can work with for a long time. So the proper way of doing it would be you derive it every single time. The improper way of doing it, I don't know, would be to just remember that x equals x0 plus vt plus 1/2 at squared. Questions about that? Great. So we actually got through. Great. Last question, and I'll let you go for lunch. So we are now not considering something falling. We're considering that something is being moved horizontally at a constant acceleration of, we don't know. But we do know the times, like we know 2 times. And so the question is, how fast was it moving initially? And how much is it accelerating? I think you're motivated to solving that because, like I said, once you're done, you can leave. No, don't enjoy that. So as I was saying, you can leave after that. I will not derive it. I will do that next time. So you sent your answer. You are free to go. So that means I should wrap this up. Questions? Questions about the format. Every Thursday or every recitation, we're going to have a quiz. Then we're going to have this interaction. Like you're going to talk to each other. I'm going to, I don't know, entertain you with anecdotes. I'm also hoping that you do have questions as we go on, because that's what this is for, right? I'm currently just assuming that guessing what kind of trouble you're going to have looking at the lecture slides. So please bring your questions with you, because you're probably not the only ones to ask them. All right? So no questions. All right, if there are no questions, I will see you next Thursday here, and I will upload the presentations by hopefully the weekend. Next Thursday is a holiday. Okay, we don't see you. But next Friday was a holiday. Well, next Thursday is a holiday. Next Friday is the bridge day. I'll see you the Thursday after. There's nobody who has to sign up, right?